You know, for years, a cosmic mystery has been hiding inside the most violent events in the entire universe, the collision of two black holes. And it's all about a single, strange clue that might just be the first real crack in Einstein's theory of gravity. And this right here? This is the clue. When scientists listen in on the gravitational waves from black holes spiraling into each other, they've been spotting something, well, weird. Right at that final moment, just before they merge, they are consistently clocked at around 53% of the speed of light. Not 40%, not 60%, but a very specific cluster right around 0.53 c. It's like there's a cosmic speed limit that, according to our best theories, just shouldn't be there.
So that's the big question, right? Why this specific speed? It's a number that has absolutely baffled physicists, and trying to find the answer is going to take us on a detective story, all the way to the very edge of what we know about space and time.
So where are we getting all this evidence? Well, from these incredible cosmic listening posts, like LIGO. For more than a decade now, they have been detecting these faint ripples in the very fabric of space-time, gravitational waves, that travel to us from these massive black hole mergers. You could say there are cosmic crime scene investigators.
And this is what the evidence actually looks like. It's called a chirp. You see, as the two black holes spiral closer and closer, they orbit faster and faster, sending out these gravitational waves that get higher in frequency and louder in amplitude. It creates this rising sound. And that final moment, right at the peak of that chirp, that's where our speed limit clue is hiding.
All right, so our first suspect. Who do we look at first when we're talking about anything to do with gravity? Well, it's gotta be Albert Einstein's masterpiece, general relativity. I mean, it's been fantastically successful for over 100 years. But when you show it this cosmic speed limit, the theory, it starts to show some cracks. So, according to general relativity, there's this thing called the innermost stable circular orbit, or ISCO. Think of it as the absolute last safe path. Get any closer, and you are doomed to merge. This concept gives us a very specific prediction for exactly how fast those black holes should be going at that final moment. And that prediction is about 41% of the speed of light for your typical non-spinning black hole. And right away, you can see the problem, can't you? We're observing 0.53 c, but our best theory is predicting 0.41 c. I mean, that's not a small rounding error. That's a huge gap. Now, okay, general relativity does have a potential explanation, but it's a bit of a stretch. To make the math work, you have to assume that most of the black holes we're seeing are spinning like crazy, near their absolute maximum possible speed, and that their spins are all perfectly aligned with their orbit. I mean, what are the odds? Astrophysically, that scenario is highly unlikely, and it really doesn't match what we observe in the wider population. The alibi is looking pretty shaky. Okay, so if our usual suspect is struggling, it's time to bring a new detective onto the case. This one comes from a pretty radical new theory of quantum gravity called the Nexus Paradigm, and it has a completely different idea of what space-time actually is. So, what is this Nexus Paradigm? Well, it suggests space-time isn't the smooth, continuous fabric that Einstein imagined. Instead, it's more like a quantized crystal. So imagine instead of a smooth ramp leading down into a black hole, there are distinct, separate steps, like the rungs on a ladder. An object can be on one rung or the next one down, but it can never be in between. And here is the crucial point. The Nexus paradigm makes a very, very specific prediction. It says that the final innermost stable orbit, that last rung on the ladder before the black holes merge, always corresponds to a specific quantum number, n equals 2. Not n equals free, not n equals 1, always 2. And that one simple idea, this idea of a final quantum state, leads to an incredibly elegant and powerful prediction. It takes this ridiculously complex gravitational dance and just boils it right down to a simple formula. The theory predicts that the speed on that final n equals 2 rung is simply the speed of light divided by that quantum number. The speed of light divided by 2. That is exactly half the speed of light. 50%, 0.5 c. And just like that, we are suddenly right next door to the 0.53 c that we actually observe in the universe. Okay, but what about that extra 3%? What gets us from 0.50 to 0.53? Well, the Nexus paradigm explains this with a really simple adjustment based on how fast the black holes are spinning. And with this one elegant little formula, it accounts for not just the base speed, but that entire cluster of data points that we see. So we have a new theory with a precise prediction. let's act like a jury here and look at the evidence. How well does this space-time crystal idea actually hold up when you put it against real-world data from LIGO? This is the fingerprint evidence. On the left, you've got the official names of real gravitational wave signals. In the middle, they're observed speeds, all clustering right around that 0.53 C mark. And on the right is the key part, the amount of spin the Nexus paradigm requires to explain that speed. And notice how they're all low, totally plausible spins, exactly what astrophysicists expect. No more need for those exotic, maxed-out spins that general relativity would require. And if you're a visual person, this just lays it all out. That solid line represents the Nexus paradigm's prediction, and it's sitting right where all the data is. The dashed line is general relativity's base prediction, and it's falling noticeably short. I mean, this visual makes it crystal clear just how much better the new theory seems to fit what we're actually seeing. So let's just summarize this head-to-head. First, the base speed. Nexus paradigm predicts 0.50 C, right where we see the data, while general relativity starts at 0.41 C. Second, how spin affects that speed. Nexus paradigm uses a simple linear relationship, while general relativity requires a much more complex one. And finally, and this is crucial, the Nexus model doesn't depend on the black hole's mass, which is what we see in the data. General relativity just struggles on all three counts here.
And get this isn't just a one-trick pony. The same Nexus paradigm theory has also been used to predict the size of the shadows of the supermassive black holes at the center of the M87 galaxy and our own Milky Way, the ones seen by the Event Horizon Telescope. And it gets them right. This suggests a unified theory that works all the way from small black holes up to the supermassive ones. So, is the case closed? Is Einstein wrong and the Nexus paradigm right? Well, in science, it's never quite that simple. We need to talk about what this all means and, what comes next. Look, the evidence we've just seen is compelling. It offers a simple, elegant solution to a puzzle that's been nagging physicists for years. But as the saying goes, extraordinary claims require extraordinary evidence. And the case against a theory as successful as general relativity is, well, it's far from closed. The final verdict is going to be delivered by the next generation of detectors. They'll measure these speeds with even greater precision. They'll be looking for events we can see in both light and gravitational waves. And as we detect hundreds more of these mergers, we'll see if the speeds continue to cluster exactly where the Nexus paradigm predicts they should. And all of this leaves us with a big question. Is this strange cosmic speed limit, this simple number, 0.53 C, is this the first real observable crack in our century-old understanding of gravity? Only time and a whole lot more data from the cosmos will tell.